Everyone looks at the recent AI breakthroughs and sees a food model, a digital chef, an AI that can tell you how to swap out eggs in a cake or what to pair with a piece of salmon. If that's all you see, you are completely missing the plot. Epicure isn't trying to beat large language models. It's doing something infinitely more important. It is proving that the next generation of AI won't just learn from raw human text. It will learn from the hidden, physical structure of the world. This isn't a recipe generator. This is a blueprint for the future of scientific AI. And if you're still thinking that AI begins and ends with ChatGPT prompts, you're already behind. Let's look at the actual technical architecture of Epicure and why it changes everything. To understand why Epicure is a massive paradigm shift, we first have to look at the foundational flaw of modern large language models. Transformers are built on text, but text only tells you what humans wrote. If you train an AI entirely on recipes, your AI learns human habits, not human possibility. Recipe data is inherently biased. It's warped by colonization, trade routes, wealth, culture, and internet search engine optimization. People cook what they know. If a dataset says that basil goes with tomato, a standard language model memorizes that correlation because it appears thousands of times in Italian recipes. But it doesn't understand why. It doesn't know that basil shares volatile aroma compounds with oregano, rosemary, and tarragon. Those molecules don't care about national borders. They don't care whether Italian or Japanese cuisine discovered the pairing first. This is the line in the sand between memorization and true structural understanding. Epicure rejects the text and asks a completely different question. What if we learn from chemistry instead? Instead of feeding billions of words into a massive, expensive transformer, Epicure uses a highly targeted data structure called a heterogeneous graph network. The entire model is compressed into a tiny, extremely dense mathematical map that is only about 2 megabytes. Think about that. A model that understands the culinary world better than a chatbot, running on a fraction of the memory. It achieves this by taking millions of recipes across multiple languages, normalizing them into just under 1,800 canonical ingredients, and building 2 distinct graph topologies. First, it builds a co-occurrence graph. This maps what humans actually do. If 2 ingredients show up in a recipe together frequently across cultures, a connection, an edge, is formed using a metric called normalized pointwise mutual information. Second, it builds the flavor DB graph. This is physical reality. It is a bipartite graph mapping ingredients directly to over 2,200 typed aroma compound nodes across 15 distinct flavor categories, like balsamic, citrus, or smoky. By separating human habit from chemical reality, the researchers created a system that can reason across both. Most machine learning models start completely from scratch with raw data and try to figure out the rules of the universe by brute force. Epicure starts with knowledge. Instead of asking the AI to discover everything through trial and error, the researchers injected human scientific domain knowledge right into the training loops using an architecture called MetaPath 2-VEC. This system uses structured, rule-based random walks across the graph to generate node sequences, which are then fed into a skip-gram objective. By dictating the exact path the random walk can take, the engineers control exactly how the AI learns. If the model takes a standard co-occurrence walk, it stays strictly on the recipe graph. It learns what humans historically match, like chocolate and vanilla. But when it takes a chemistry walk, the path is constrained strictly to cross-type compound paths, ingredient to compound to ingredient. The walk doesn't know what a recipe is, it only knows which ingredients share molecular structures. This allows it to discover that chocolate matches brilliantly with things like toffee, fudge, or even blue cheese. By blending these paths with a hybrid metric, the researchers created a model that strikes a perfect balance between culinary culture and chemical reality. The winners of the next wave of AI won't have the biggest models or the most GPUs. They will have the best structural priors, When these graph walks are embedded into a 300-dimensional vector space, they exhibit incredible geometric properties. In data science, we look closely at a concept called isotropy, which basically measures how uniformly distributed vectors are across a space. The pure chemistry embeddings in Epicure have an incredibly high participation ratio and a very low average pairwise similarity. This means the space is highly isotropic. The concepts spread evenly across the mathematical sphere, preserving strict chemical definitions without human cultural bias pulling them together. But when the researchers inject human recipe data, the space collapses slightly, creating emergent dense clusters where culinary concepts, textures, and regional macro cuisines become linearly recoverable. The AI isn't just predicting the next word in a sentence. It has built a geometric map of the physical world. The true mathematical magic of this architecture comes alive during inference. If you've ever seen classic vector math, you know the famous example, king minus man plus woman equals queen. Standard models do this using linear interpolation. They draw a straight line from point A to point B. But high-dimensional embedding spaces are curved. They are hyperspheres. If you draw a straight line across a sphere, you cut through the empty, unmapped void of the center, where the AI has no data. This is where models hallucinate or output mathematical garbage. Epicure solves this by implementing Spherical Linear Interpolation, or SLERP. Instead of cutting through the void, SLERP walks smoothly along the surface of the 300-dimensional hypersphere. It treats the latent space like a globe, rotating continuously between concepts. Imagine giving the AI a steering wheel instead of a teleportation device. By initializing a vector at a base ingredient and applying a directional rotation toward a target concept, like a specific cuisine, the model smoothly navigates culinary space. If you take the vector for corn and rotate it 30 degrees toward a Latin American cuisine vector, the model outputs poblano pepper, corn tortilla, salsa, and Monterey Jack. It isn't looking up hard-coded pairs. It is continuously dialing an ingredient into a new cultural or structural context without losing its core identity. Here is the ultimate takeaway, and the reason why this matters far beyond the kitchen. An ingredient graph is structurally identical to a metabolic pathway in a cancer cell. It is structurally identical to an interaction network between proteins, a dependency map in a global supply chain, a network of cybersecurity vulnerabilities, or a financial fraud ring. Once you master how to embed a graph, map its latent space, and navigate it smoothly using geometric interpolation, you haven't just built a digital chef. You have built a foundational engine for scientific discovery. Notice the macro pattern happening across AI research right now. We are moving away from text and toward knowledge graphs, away from documents and toward scientific databases, away from language and toward physical reality, away from basic prediction and toward reasoning over structured domains. The frontier is no longer just about building bigger chatbots to write better marketing emails. The frontier belongs to domain-specific foundation models built on structured scientific knowledge. The people who understand graphs, geometry, embeddings, and knowledge representation are the ones who will build the next generation of computing. The framework is universal. Food was just the demonstration.